Fundamental. It's this question you hear sometimes, it sits right at the heart of quantum physics and, reality itself. It's this. Is a quantum of energy defined by the Planck length? Now, look, the simple answer, the quick one is just no.
Right.
But, that's where it gets really interesting. Because the deeper story, how these two things that seem separate actually collide, well, that's way more profound, more exciting than just yes or no. So this deep dive, that's our mission today. Unpack that relationship, explore the absolute limits of, well, what we think we know about physics.
Absolutely. And just to be clear right from the start, a quantum of energy, fundamentally, that's tied to Max Planck's constant h in frequency. It's like the smallest possible chunk of energy you can have at a given frequency. The Planck length, that's something different. It's a unit of distance, incredibly, incredibly tiny. It's the scale where we think space-time itself might get, grainy. Not smooth anymore.
Grainy, okay.
Yeah. But our mission, as you said, is to explore where these two ideas actually meet. That point of synthesis, this extraordinary scale where everything changes.
Okay, so let's dig into that first idea then, quantized energy. Because it wasn't just
A group.
dreamed up,
Right.
right? It came out of a genuine crisis in physics, late 19th century. They called it the ultraviolet catastrophe. Sounds dramatic.
It was pretty dramatic for physics at the time.
Yeah, imagine heating something up like a lump of metal.
Yeah.
Classical physics, specifically something called the Rayleigh-Jeans law, it predicted something absurd. It said the object should just keep emitting more and more energy, infinitely more, especially at high frequencies like ultraviolet light.
Which obviously doesn't happen. Things don't glow infinitely bright in UV just because they're hot.
Exactly. Total mismatch with reality.
Right.
So December 14th, 1900, Max Planck, he kind of, in what he later called an act of despair, he proposed something completely radical.
Yeah.
Energy isn't smooth, it's not continuous, it's exchanged in these little discrete packets, these energy elements. And just like that, fitting his math to the data, he basically kicked off quantum mechanics.
And the heart of that solution, the definition of that quantum, is E equals hf. E is the energy, F is the frequency, and H is that all-important Planck constant, about 6.626 times 10 to the minus 34 joule seconds. Tiny number, huge implications.
Quantum of action, right?
That's it, the fundamental graininess. Now, Planck originally thought of it maybe more as a mathematical fix, but Albert Einstein, in 1905, he took the really big leap. He said, these quantas aren't just about how energy is exchanged, they are fundamental particles of light. Photons.
The photon itself.
Exactly.
Yeah.
And the killer evidence was the photoelectric effect. You shine light on metal, electrons pop out. But it turns out what matters is the frequency of the light, the energy of each individual photon, not just how bright the light is.
So like dim blue light could kick electrons out, but super bright red light might do nothing.
Precisely, because each blue light photon, higher frequency, carries enough energy, EREF, in one packet. The red light photons, lower frequency, just don't have the necessary punch no matter how many there are. And this whole idea of quantization is everywhere. Think about atoms. Why don't electrons just spiral into the nucleus?
Good question. Classical physics said they should.
It did, but they don't because their energy levels are quantized, like specific rungs on a ladder. They can only exist on the rungs, not in between.
Okay.
And they jump between rungs only by absorbing or emitting a photon with exactly the right energy difference. Delta E equals HF again. So that constant H, it dictates the resolution of reality. From light to atoms, even underlies the Heisenberg uncertainty principle.
Wow. Okay, so that's the quantum of energy, deeply tied to H. Now let's pivot. Let's talk about the Planck scale. You said it wasn't from a paradox, but more like a cosmic recipe.
Yeah, that's a good way to put it. It comes from dimensional analysis. You take the universe's absolute bedrock constants, speed of light, c, Newton's gravitational constant, g, and the reduced Planck constant, E, which is just h divided by 2 pi.
Right.
And you combine them in the only way possible that spits out a unit of length. And what you get is the Planck length, LP. It's staggeringly small, about 1.6 times 10 to the minus 35 meters.
Okay, 10 to the minus 35. That's hard to grasp.
Yeah.
The analogy in our notes is pretty wild. If a proton, just one proton, was blown up to the size of the entire observable universe, the Planck length would be like, what, the distance of a flight from Tokyo to Chicago?
Something like that, yeah. It's just an utterly alien scale compared to our experience.
Yeah.
And from those same constants, you also get Planck time, about 10 to the minus 44 seconds.
The time it takes light to cross a Planck length.
Exactly. And Planck mass, which is weirdly not that small, about 22 micrograms, like a flea's egg, apparently.
Huh. Why is that one relatively large? We'll get to that maybe.
We will. It relates to gravity's weakness. But the Planck length, its significance is profound. It's seen as the theoretical boundary, where our two main pillars of physics, general relativity for gravity and large scales, and quantum mechanics for the small stuff, they just don't work independently anymore.
They have to merge somehow.
Have to merge. The smooth, continuous spacetime of general relativity is expected to break down. It becomes grainy, like you said. Think about this thought experiment. Say you want to see something as small as the Planck length. You need a probe with a tiny wavelength, right?
Which means incredibly high energy because E hole, shorter wavelength lambda, higher energy E.
Exactly. Immense energy.
Yeah.
But Einstein also told us EMC squared. That energy has an equivalent mass. And general relativity tells us if you pack enough mass into a tiny space,
You get a black hole.
you get a black hole.
Yeah.
And it turns out the energy needed to probe the Planck length is precisely the energy whose equivalent mass would create a microscopic black hole with an event horizon roughly the size of the Planck length itself.
Whoa. So trying to look smaller than the Planck length.
Just creates a black hole that hides what you're trying to see. And if you use even more energy to try and probe smaller, you just make a bigger black hole.
So nature itself stops you. There's like a fundamental limit to resolution.
It certainly seems that way. It's like a cosmic censorship built into the laws of physics. This scale also defines the earliest moment in the universe we can even talk about, the Planck epoch. Before that, our physics just gives nonsense. And back in 1955, John Archibald Wheeler had this vision of space-time foam. He pictured space-time at this scale not as smooth, but as this incredibly turbulent, fluctuating sea of quantum uncertainty. Tiny wormholes popping in and out of existence, virtual particles, a real mess.
Like a quantum ocean boiling.
Kinda, yeah. Now, could we see effects of this foam? Some models predicted it might slightly slow down very high-energy photons traveling across cosmic distances compared to lower-energy ones. A tiny violation of Lorentz invariance, the idea that the speed of light is constant for everyone.
Okay, so we looked for that with things like gamma-ray bursts.
Exactly. They're incredibly energetic events. Light travels for billions of years to reach us. Perfect test case. But the results, especially from a big study in 2022, came back null. No delay detected, down to very high precision.
Huh. So that put some constraints on those specific foamy spacetime models.
It did. Significant constraints. Doesn't rule out quantum gravity, but it does challenge some specific pictures of how spacetime might be granular.
Okay, so now let's bring these two threads together. The quantum of energy, EH, and this Planck scale granularity. You mentioned the Planck energy is the bridge.
Yes, the Planck energy, EP.
And the weird thing, as you hinted, is how big it is. Roughly 2 billion joules. Comparable to the energy in a tank of gas. That seems massive for a fundamental energy unit.
Yeah.
How does that arise from tiny constants?
It does seem paradoxical, doesn't it? And the reason boils down to just how incredibly weak gravity is. Remember, the Planck mass was relatively large. It takes a lot of energy concentrated in one place for gravity's quantum effects to become comparable to the other forces. But this is where the real synthesis happens. Let's imagine that Kugelblitz, the ball lightning thought experiment again. Take a single photon. Keep cranking up its energy.
Okay.
As its energy E goes up, its wavelength lambda shrinks. When its energy hits the Planck energy, EP, its wavelength shrinks precisely to the Planck length, LP.
Right down to that fundamental limit.
And its energy via EAC Planck corresponds to the Planck mass, MP. Now plug that Planck mass into the equation for a black hole's Schwarzschild radius the size of its event horizon.
What do you get?
You get the Planck length.
No way.
Yes way. The photon with Planck energy confined to its own wavelength becomes a black hole whose size is the Planck length.
So at that ultimate limit, the particle is the black hole. The quantum of energy is the space-time distortion.
The distinction dissolves. They become one and the same entity. So in that very profound sense, the initial intuition isn't entirely wrong. The Planck length does define the nature of a quantum of energy, but only at the Planck energy scale.
That's incredible. It's like quantum mechanics and general relativity are forced to shake hands right there.
Precisely. And this is also the energy scale where physicists believe the four fundamental forces, strong, weak, electromagnetic, and gravity, were unified into a single superforce. Back in the Planck epoch, the very first instant after the Big Bang.
But getting there experimentally.
Yeah.
You mentioned the energy desert.
A vast desert. The Planck energy is around 10 to the 19 GeV, gigaelectron volts. The Large Hadron Collider, our most powerful machine, it reaches about 10 to the 4 GeV.
That's 15 orders of magnitude short. 1,000,000,000,000 times less energy.
Yeah. A collider powerful enough to reach the Planck energy directly would need to be, well, impractically large. Think bigger than the solar system. Even the most energetic particles hitting Earth from space, cosmic rays, they fall far, far short.
Okay, so direct tests are out for the foreseeable future. Which brings us to the theories. How do things like string theory or loop quantum gravity try to describe this Planck scale reality if we can't poke it directly? You mentioned they seem to converge on some common ideas.
They do, remarkably. It's all about trying to build a framework where quantum mechanics and gravity can coexist. And they often end up talking about geometry, information, and the Planck area in surprisingly similar ways.
Let's start with black holes. You mentioned entropy.
Right. Jacob Bekenstein back in the 70s argued black holes must have entropy. Stephen Hawking then showed they radiate and derived the Bekenstein-Hawking formula for that entropy. The striking thing is the entropy isn't proportional to the black hole's volume, but to its surface area.
The area of the event horizon.
Exactly. And the formula relates this area directly to the Planck area, which is just the Planck length squared, LPLA. It strongly suggests the event horizon is sort of tiled or pixelated with these Planck area units.
Like each tiny square holds a bit of information.
That's the interpretation. Roughly 1 bit of information per 4 Planck areas. It was a huge clue. Maybe information is fundamental, and geometry at the Planck scale is discrete, built from these informational bits.
Okay, so that's one angle. What about string theory?
String theory takes a different approach. It says the fundamental entities aren't point particles, but tiny vibrating strings, roughly Planck length in size, maybe 10 meters. And the way these strings vibrate determines what particle we see. Different vibration modes look like an electron or a photon or a quark. Crucially, one specific vibration mode corresponds to the graviton.
The hypothetical particle that carries the gravitational force.
Precisely. So in string theory, gravity isn't something you add on later, it's an inherent consequence of these vibrating Planck scale strings. Quantization and gravity are merged together.
Okay. And loop quantum gravity, or LQG, how does that differ?
LQG tries to quantize spacetime itself directly. It doesn't assume a background spacetime like string theory often does. Instead, it says spacetime is built from fundamental discrete units. It uses structures called spin networks. Think of them like webs or graphs where nodes represent tiny chunks of quantum volume, and the links connecting them represent quantum areas.
So space itself is like
Yeah.
Lego bricks at the bottom.
In a way, yes. The most profound prediction of LQG is that geometry itself is quantized. Area and volume can only exist in discrete multiples of Planck units, specifically related to the Planck area. The smooth space we see is just an approximation, like looking at a woven shirt from far away, you don't see the individual threads.
Got it. And the last one you mentioned, the holographic principle, that sounds pretty sci-fi.
It is wild and still quite speculative, but it also grew out of black hole studies. The idea, pushed by people like Gerard Hooft and Leonard Susskind, is that all the information needed to describe a volume of space can actually be encoded on the boundary surrounding that volume, like a 2D surface holding all the info for a 3D region.
Like a hologram. A 2D film creates a 3D image.
Exactly that analogy. It suggests that the maximum amount of information you can cram into a region is proportional to its surface area in Planck units. Again, about 1 bit per 4 Planck areas, not its volume.
Which would mean?
The staggering implication is that maybe our 3D reality is fundamentally an illusion, a projection from a lower dimensional screen operating at the Planck scale. It puts information as potentially the most fundamental thing in the universe, with space-time and everything in it emerging from that information.
Wow. Okay, so despite completely different starting points, black hole thermodynamics, vibrating strings, quantizing space itself, holography, they all seem to point
towards a discrete space-time at the Planck scale, and this fundamental role for the Planck area, often linked to information. It's a remarkable convergence, suggesting we might be circling around some deep truth about the equivalence of geometry and information at the very foundation of reality.
It sounds like an incredibly rich theoretical landscape. But, like we said, testing it. That's the elephant in the room, right? That huge energy desert. So what's the plan? How do physicists try to bridge this gap between these amazing theories and actual experimental proof?
Yeah, that's the grand challenge. Direct tests being impossible for now, the focus is on indirect evidence and clever, high-precision experiments. One avenue is looking for relics from the early universe, those cosmological observations, like searching for specific patterns called B-modes in the polarization of the cosmic microwave background radiation. These could be faint signatures of gravitational waves produced during the inflationary epoch, which happened near the Planck time. Seeing them would give us a window into physics at incredible energies.
Okay, looking back to the beginning, what else?
Then there's the continuing search for tiny deviations from known physics, like those potential violations of Lorentz invariance from space-time foam we talked about.
Even though the gamma-ray burst results were null.
Exactly. Those null results were crucial. They didn't kill quantum gravity, but they ruled out, or at least severely constrained, specific models, particularly some versions of LQG that predicted a detectable effect. It forces theorists to refine their models.
So that leads to maybe different kinds of experiments.
It does. There's been a real strategic pivot towards high-precision tabletop experiments. These don't need huge energies. Instead, they look for subtle quantum effects of gravity here and now.
Like what?
One exciting area is called gravity-induced entanglement, or GI. The idea is to take two tiny but still macroscopic objects, maybe microdiamonds or something, and put each one into a quantum superposition, meaning it's in two places at once.
Like a standard quantum weirdness.
Right. But then you place them near each other. If the gravitational field they generate is itself quantum, then it should also exist in a superposition. And that quantum gravity field should then entangle the two objects.
Entangle them, meaning their fates become linked even if they're separated?
Exactly. If you could experimentally show that gravity alone can cause entanglement, that would be definitive proof that gravity is quantum without ever needing to reach the Planck energy. It's a very clever way to probe the quantum nature of gravity indirectly.
That sounds promising, but still incredibly difficult, I imagine.
Oh, absolutely. Technically extremely challenging. But it represents a shift towards testing fundamental principles rather than just reaching high energies.
But this difficulty in testing, it leads to a kind of tension, doesn't it? Almost a philosophical debate within physics.
It really does. Both string theory and loop quantum gravity have faced some pretty sharp criticism precisely because many of their most distinctive predictions are so hard or currently impossible to test.
What's the issue with string theory specifically?
The big one is the landscape problem. String theory doesn't seem to predict one unique universe. It seems to allow for a vast number, maybe 10 to the power of 500, or even more possible universes, each with slightly different laws or constants.
So how do you know which one is ours? How do you make a testable prediction?
That's the problem. If your theory allows for almost anything, it's very hard to prove wrong, to falsify. Critics argue it becomes more like a mathematical framework than a predictive physical theory in the traditional sense.
And for loop quantum gravity, the issue was the Lorentz invariance prediction that didn't pan out.
That was a significant blow for some versions of LQG, yes. It had offered a potentially clear, observable prediction, and the null results from gamma-ray bursts were quite definitive. Some critics called it a major failure for that line of research. It caused a bit of a split within the LQG community itself. Some researchers argue that Lorentz invariance violation wasn't actually a core prediction of the fundamental theory anyway, while others had championed it. Critics see this sometimes as, well, moving the goalposts when a prediction fails.
So it creates this really deep question about what makes a theory scientific. If you can't test it, or its predictions keep shifting.
Exactly. It hits this philosophical impasse. How much weight do you give to mathematical elegance, internal consistency, the potential to unify physics, versus the traditional scientific bedrock of empirical testability and falsifiability?
There are strong arguments on both sides, I guess.
Yeah.
Pursuing the math versus needing the experiments.
It's the central tension at the absolute frontier of fundamental physics today. People are grappling not just with equations, but with the nature of scientific knowledge itself. What does it mean to understand the universe at its deepest level if we can't actually experiment there?
So let's try and bring this all together then. We started with what seemed like a simple question. Is a quantum of energy defined by the Planck length? And the journey we've taken shows, well, in our normal world, at low energies, they're distinct ideas. H for energy quanta, LP for a length scale.
Yeah.
Push things to the absolute limit.
And they profoundly connect. At that ultimate scale, the Planck energy, the quantum, becomes the distortion. The particle is the black hole. The distinction just vanishes. It's a beautiful, challenging synthesis. And what's truly remarkable, I think, is how these different paths towards quantum gravity, whether it's black hole thermodynamics, strings, loops, or holography, they all keep bumping into the same core ideas. A discrete structure to space-time at the Planck scale, and the Planck area playing this fundamental role possibly as the basic unit of information.
A convergence suggesting there's something real there, even if the final picture is still fuzzy.
Exactly. The challenges, both theoretical and experimental, are immense, no doubt about it. But the picture emerging is one of a universe that's ultimately granular, informational, and unified in ways we're only just beginning to grasp.
It really is amazing how that quest that started with Max Planck just trying to fix a problem with light bulbs, essentially.
Pretty much.
Has led us right to the ragged edge of reality itself, where the chunkiness of energy, the graininess of space and time, they have to somehow merge into one single, unified, quantized picture. So maybe the thought to leave you with today is this. Ponder that deep connection. Geometry, the shape of space and time, isn't just a stage. It seems to be profoundly linked to information, the fundamental bits that make up reality, all playing out at these almost impossibly small fundamental scales. What does it really mean for the nature of everything?